Okay, so this is sort of a practical talk about how to learn Koopman operators from data. And as I said, I mean, having the opportunity to talk to this group about Koopman is, as I said, like talking to Messi about soccer. So, okay. Let me tell you why. I mean, obviously, you don't need any introduction to Koopman. Let me tell you why I got interested. I started looking at Koopman for some computer vision applications where I had to do nonlinear SID, which it's a non-solved problem, and Koopman provides a very nice framework. But to me, more interestingly, is that if you look at what happens in machine learning, a lot of people have started to look at Koopman-based architectures for learning dynamical systems. I mean, neural nets are great for classification, for regression, blah, blah, blah. But when they were trying to learn dynamical systems, they tried to use, for instance, LSTMs, which may or may not work. They have lots of ad hoc parameters, et cetera, et cetera. And then people start thinking, wait a minute, maybe we can use a Koopman-based approach to give some interesting structure that actually has a nice interpretable connection with the dynamics. And I mean, there's a paper by Lush and her group that's a few years old by now. There's a very interesting paper by Sam Motto and Clancy Rowley about LRAN architectures and so on and so forth. And the truth of the matter is that this works. The thing that bothered me a little bit is that they have many ad hoc choices. Typically, they are based on extended dynamic model decompositions. So you have to pick the right dictionary, you have to pick the right dimension for your observables, perhaps the space where your observables live, and so on and so forth. And that's largely a trial and error type approach. And then at the end of the day, once you pick your dictionary and do your thing, well, Koopman operators sometimes tend to be infinite dimension, unfortunately, and you're doing a finite dimensional approximation, and we don't even know anything about the approximation effort. Okay, so I got interested into this, and the interesting thing is that a lot of those questions can be answered by using a combination of probably simple tools from interpolation theory to recast the problem into some convex semi-definite programs. Okay, so just as a spoiler, I mean, I call this a network and architecture. It's not really a network. It's just so that when I present this to people in machine learning, they immediately make a connection. So the idea is that you have your states, you solve a semi-definite program, you get what people in machine learning we call the latent variables and the embedded manifold, we call those the observables. Then you do some SID on the manifold, you get your model, and then you will get your, again, what machine learning people will call your decoder that takes you back from the observable space to state space. And that's going to be another semi-definite program. Okay? So as I said, I mean, you have an encoder and decoder on each end. That's essentially projections to and from your manifold, and kernel-based SID on the manifold. And the fact that you have convex SDPs and kernel-based SID gives you manageable complexity, because that's a problem. If you have lots and lots of data points, trying to actually make this work, it's not trivial. One interesting thing about this is that you can get a worst case approximation error by looking at the kernel that you get. Essentially, the smallest singular value gives you the how close you are to approximating the true operator, or at least on the manifold. But more interestingly, I mean, there are almost no ad hoc choices, in the sense that the dimension of the embedding manifolds, or if you wish, of the observables, the order of the dynamic of the linear dynamics, they come straight out of the math. Of course, I mean, a little bit disingenuous, because that's true, but there are some magic hyperparameters that you have to play with, and you'll see that. But those hyperparameters have a very definite meaning, and they're easier to choose than just picking dynamics order or the order of your embedding manifold out of the blue. Okay, so I'm going to go through 2 introduction slides. I know that everyone in this group knows this, but maybe there's someone in the audience from machine learning. So anyway, Hankel matrices, something we teach our students in Control 101 or State Space 101. If I give you the output of a linear time invariant system as a time series, I Hankelize the time series. The rank of the Hankel matrix is the order of the minimal realization that you need to realize this system. Okay, well known in Control, well known in SysID. Something that's a little bit less known, it's what's called the Loewner matrix. Suppose that I give you points and I ask you to find a rational function that interpolates your points. What is the order of the minimal rational function? Turns out that if you create this Loewner matrix, which is a sort of, you can see the divided difference matrices, there exists a rational interpolant if and only if this matrix is rank deficient. And the rank of that interpolant, of that matrix, gives you the minimum order of the interpolant. Okay? In realization theory, this is typically used in the frequency domain. When I give you frequency domain points and you're trying to find the transfer function. So Hankel will be time domain, Loewner will be what you do in the frequency domain. There's a very interesting connection between Hankel and Loewner. I won't go into this. In this specific talk, I'm going to work only the time domain. So I'm going to use Loewner and Hankel in the time domain. Okay. So the way I'm going to find the Koopman operator is actually, first I'm going to find the embedded manifold. So I'm assuming that I don't know what the observables are, and I'm trying to find observables that are in a manifold where dynamics are linear. And then I'm going to worry about how do I go from state space to observables and back. Okay. So since we want to find latent variables that have the underlying dynamics is low dimensional, I mean, it's natural to minimize the rank of the Hankel matrix or look for Hankel matrices that have low rank. However, if I were to do that, I mean, the Hankel matrix has the y's in there, which means that in order to build the Hankel matrix, I will have to decide a priori how tall y is. In other words, I have to decide the dimension of the embedding manifold. And I don't want to do that. So instead of working with the Hankel matrix, I'm going to work with the Gramian matrix, H transpose H. Obviously, the rank of G and the rank of H are the same. So if I make G rank deficient, I found my linear dynamics. But one of the advantages that I have working with G is the fact that now you recognize this as a kernel. I have only inner product. So I don't have to worry right now about the dimension of Y. We'll worry about it later on. And also I get much smaller matrices, which imply much smaller semi-definite programs. So also has a computational advantage. Okay. One judgment call that I need to make now is that I have to decide either to preserve the local geometry in the embedding or put Lipschitz bounds on the Lipschitz constants on the mappings from ambient space to the observables. Because if I don't do that, I get ill-post problems. Everything goes to 0. Okay. So as a preview, this is the type of things that I get when I'm trying to find the embedding manifold. So I have an objective that has a rank and a trace, and then I have a bunch of constraints. K has to be positive semi-definite. I have some other constraints in there. Okay, what does all of this mean? So let me go step by step on what everything means, right? Obviously, we didn't come up with this and then decide what everything means. I mean, you obviously do things backwards. You wow the audience with this and then explain how to get there. So this is essentially spatial information. What I'm imposing here is I want for a neighborhood of my states that the spatial geometry be preserved. In other words, if I have points in state space that are close, I want their projections on the manifold to be at the same distance. And I'm doing this for simplicity. I mean, you could put bounds and you could put Lipschitz constants. It really clutters the slide and doesn't add anything. Okay. Now, in here, you can see one of the advantages of working with kernels, because if I were to leave it like the equation on the right-hand side, that's non-convex, right? I mean, quadratic equals quadratic is non-convex. On the other hand, if you expand yi minus yj distance squared in terms of the inner products, you get the equation on the left that's linear in your variables. Okay. Why do we want trace k here? I mean, I'm minimizing minus trace, which means I'm maximizing trace. This is an old idea that came from a paper from Saul and Rowis. It's about now almost 20 years old. It's called semi-definite embeddings. And what you're trying to do here is to promote low-dimensional embeddings. The idea is that if you maximize the trace of k, you're spreading your points around in the manifold. It's like you take a piece of paper and you sort of pull, which tends to flatten the manifold and give you lower dimensional embeddings. It's a heuristic, but it works really well. Okay. How about the other terms in here? G, it's the Gram matrix. So the reason for minimizing the rank of G is because you want low order dynamics. You want your Koopman operator to be low order. Okay. And we already said that G has to be H transpose H. But what becomes really interesting is that if you actually take the time to compute H transpose H, you get a sum of the elements of submatrices of your total kernel matrix. I mean, it's tedious, but all you need to do is write HY transpose HY in terms of other products and just sum, and you get something like this. And this is interesting because now it turns out that everything in here is affine in the elements of the kernel matrix. I mean, G matrix, it's an affine function of your kernel matrix. Your constraints are affine in the elements of the kernel matrix. So except for the fact that I have rank, this is now a semi-definite program. So how do we handle rank in semi-definite programs? We remember, I mean, what Marian Fassel did, and we use the fact that the convex envelope of rank, it's for a symmetric matrix is trace, otherwise it's nuclear norm. And then you get something that looks like this, right? Couple of things in here. This is a little bit crude. You could do better if you want using the reweighted heuristics for rank. So instead of trace of G, you put nuclear norm of WG and you do a couple of iterations. But this has worked surprisingly well for me. Okay. What happens after you solve? After you solve, you take your kernel matrix and you do a Cholesky factorization, and the columns of Y are exactly the manifold projections that you're looking for. And from here, you immediately see that the rank of K gives you the dimension of the embedding manifold. And that's the reason why we're minimizing the rank, or in this case, we're maximizing trace of K. And then you take your G, you do either Kalman-Ho or any subspace ID, and from there you get your dynamics. That would be your Koopman operator. A couple of comments here. I'm minimizing the rank of G, but as long as I get a G that's rank deficient, it may not be the minimal Koopman operator or minimal dynamics, but it's a valid dynamics. So all you need is to have G rank deficient, and then you're certified to have linear dynamics in your manifold. Now, what happens if G is not rank deficient? The smallest singular value of G tells you how close you are to a rank deficient matrix. There's a very interesting property that it says that if you have something that has a Hankel structure, then the smallest singular value gives you the closest distance to something that also has Hankel structure. In other words, PCA works also with Hankel structure. Okay, so we got a couple of good things from here. We got the order of the dynamics, we got the order of the dimension of the embedding manifold, and we got also the bound on the error of how close we are to potential and infinite dimensional linear dynamics. Okay, this is just to show you that even without getting the mapping from state space to observables in an explicit way, you can actually find what your observables are. Okay? What are the implications of this? There are many, many problems where you don't really care about the explicit function that takes you from state space to latent variables. Let me give you an example. As I told Igor, I'm in love with the paper that you guys are doing about using the spectrum of the Koopman operator to check training of neural nets. For that, I don't care about the mapping from state space to the actual parameters of the neural net. All I care is about the spectrum of the Koopman operator, which I can get this way without bothering to find the sort of the encoder and the decoder. So same thing happens in a lot of problems when you have to do anomaly detection, and I'll show you a couple of examples. Okay? Now, in some other cases, you're actually interested in finding the mapping from state space to observables and back, right? I mean, if you're trying to do control, if you're trying to do reconstruction of an image or video sequence, you want to find the mapping. Okay? So first, I mean, a technical point, since I already forced my mapping to be Lipschitz continuous through the constraints, I can always assume that the mapping is rational. I mean, just stone Weierstrass it to death, assuming that you stay inside a compact set. And then all I need to do is I can use now Loewner interpolation to find a mapping a rational mapping that goes from state space back to the observables. One of the things you notice in here is that I'm doing Loewner not on X and Y. I'm doing Loewner on the kernel of X and the kernel of Y. And you'll see why in a minute. But this actually works much better. And since X is given, the two things can happen. If I already know the kernel of Y because I found it before, then all I need to do is compute the node space in here. But this may give me some more degrees of freedom to play with. Okay? So suppose that I have many different choices for my variables in the manifold. So instead of just solving the optimization problem that I showed you before, maybe I can add an extra term here where I minimize also the rank of Ly. Okay. What do I get from this? Well, I mean, I'm going back to the state space, it's sort of the inverse problem. I mean, just compute the Loewner matrix for the kernels of X given Y. So what happens in here is for the predictions, you'll do your prediction in the latent space, and then you will minimize the rank of this with respect to the element of the kernel of X that you don't know, which is the next state in state space. And that gives you the overall prediction of where your state should be. Okay. Coming back to the point I had before, one of the things I can do is add this extra term in my objective that also seeks to penalize complicated interpolants if I need to. Okay, it's up to you. So here are the hyperparameters that I mentioned before that you have to select, but the physical explanation of the hyperparameters is that lambda is a trade-off between the dimension of your embedding manifold and the order of your dynamics. I mean, intuitively, you can have a very low order manifold. I mean, project everything to align to a trajectory, but your dynamics there are going to be very complicated. Or an extremely high order embedding manifold with very simple dynamics. And lambda is a trade-off. Okay. And mu, in case you're interested, it's some sort of trade-off if for some reason you want to have low order, or I mean, you want your encoder and your decoder to be low order interpolants. But typically, you don't really use mu too much, right? So as I said, at the end of the day, you have one quad encoder, which is the SDP that projects to the manifold, linear dynamics in the manifold, and quad and decoder and quad that takes you back to the state space. Okay, so all the theory is great. You can come up with small examples that you can solve, like we do to get our paper published in CDC, right? But let's get real. I mean, I want to sell this to a machine learning people, or I'm working with colleagues in computer vision and they want to use this to be able to analyze video sequences, predict what's going to happen next. For instance, you want to use this in an autonomous car and you want to analyze a scene and see if someone is going to jump in front of your car or not. And in there, now we're talking about thousands of points in pixels. So if you have any experience trying to solve semi-definite problems, you know that things pretty quickly becomes untractable. So can we push this beyond some nice simple examples? I mean, can we actually solve this in some semi-decent size problems? And as it turns out, you can do that because the semi-definite problems that you have, they are not just any random semi-definite problem. They have a hidden structure that you can use to bring down your computational complexity. So let me talk a little bit about how to actually solve structured semi-definite problems. Okay. So I'm going to talk about a different problem, and then I'm going to connect both of them. The problem that I want to talk about is positive semi-definite matrix completion. So suppose that I give you this matrix that's symmetric, but it's missing a few entries. Those question marks are elements that are variables that you don't know. And I ask you two questions. Can you complete this matrix to be positive semi-definite? And if you can, what is the rank of the minimum rank achievable for the completion? Okay? Obviously, you say, well, I know how to solve this problem. Just let me write 4 lines of code in CVX, and I'm done. And if I'm interested in minimum rank, then I'll use the pre-weighted heuristic, blah, blah, blah. But what's interesting in here is that you can actually solve this problem without having to do any computations. And how do you do that? Okay, so here's the idea. You take your matrix, and to your matrix, you associate a graph. That's called a correlative sparsity graph. You have one node per row or column on your matrix. And then you have an edge if the variable is given. So for instance, in here, you'll see that I have an edge that joins 1 and 2. That's because the variable x12 is given to you. By the same token, I don't have connection between 1 and 3 because x13 is a free variable. Okay? All right. What does this have to do with matrix completion? And here's the idea. You take your graph and you do a click decomposition on your graph. You decompose your graph into clicks. Okay? There's a technical issue here. In order to be able to do that, you need your graph to be chordal, meaning that every cycle has to be at most of dimension 3. Those are called triangulated graphs. It's not a big deal. If your graph is not chordal, you can add additional edges. I mean, which means that some of your variables become optimization variables. But the good thing about chordal graphs is that you can do a click decomposition in polynomial time. So for the graph that I have here, here are my clicks. And they're color-coded. Each click here corresponds to a submatrix of your original matrix. And here's an interesting theorem. It's a Grom's theorem that says that your matrix can be completed to be positive semi-definite if and only if, when you compute the submatrices on the clicks, those are positive definite or positive semi-definite. Which means that you don't have to solve an optimization problem. I mean, you do the click decomposition, but then you just only need to check if things over the clicks are positive semi-definite. And then there's another theorem called Dancy's theorem that says, by the way, the minimum rank that you can achieve is the maximum rank over the clicks. Obviously, the maximum rank over the clicks, it's a lower bound. But what's interesting about Dancy's theorem is that it shows that the lower bound is actually achievable. Right. So let me bring this down to earth a little bit. How do you use this to solve or simplify semi-definite problems? Here's a toy example. I want to minimize x14 subject to this condition, x12 plus x13 plus x23 equal 1, right? If you notice in here, there are some variables that do not appear neither in the objective nor in my constraints. For instance, x24, nowhere to be seen, right? x34, nowhere to be seen. Those are variables that I only need to make sure that I can complete my matrix to be positive semi-definite, but I don't need to know their values. I only need to know that they exist. And here's where Grom's theorem comes into play. The only variables I really need are x14, x12, x13, x23. So x14 is in here, x12, x13, x23. This is a relevant graph. And then I can do a click decomposition on this graph, and I get that this matrix in here is positive semi-definite if and only if those two matrices are positive semi-definite. Which means that when I write my SDP, I don't need to write this SDP in terms of this larger matrix or have those extra variables. My SDP involves this objective and those two conditions. Why is this important? Because it's well known that if you use interior point methods to solve semi-definite problems, complexity scales horribly, truly horribly, with the number of variables or the size of the maximum matrix. I mean, it's like n power 5 or n power 6. So very quickly, you run out of steam. You just try one big constraint. But if you do click decompositions, then we're in business. You can handle much larger problems, provided that they have some sort of sparsity built in. Okay? So let me come back to this problem we're trying to solve. If you actually dig in a little bit, what you're going to find is that the correlative sparsity graph has number of data points squared because it corresponds to the variables in the kernel matrix. However, it's very sparse in the sense that when you look at the constraints here or the objective, you can show that the things that are relevant are either spatial neighbors, things where you choose to preserve the local geometry, or things that are temporal neighbors, like which depends on the order of your dynamics. So at the end of the day, you can do a click decomposition on the SDP that I have, where each click has the spatial neighbors plus the temporal neighbors. That's all you need, and you don't care beyond those horizons. Okay? So not only this brings down the computational complexity substantially, it also tells you what makes your problem difficult. If your local points are tightly connected, in other words, if you want to preserve the local geometry over very large domains, or if you want high order dynamics, you're in trouble. Because that means that your clicks are very large and your computational complexity is going to be horrendous. But if you have small domains where you want to preserve the local geometry, or the dynamics are low order, then the SDP is not that bad, provided you use this. I mean, if you use the original SDP, you die a horrible death. Okay? So, I mean, this is important. The fact that having temporal ordering and spatial domains actually imposes this hidden sparse structure. Okay, so examples. No Koopman talk will be complete without using the Lorentz oscillator. So all I want to say in here is that I got 7-order linear dynamics. And here's how I did this experiment. I trained with the black crosses. Then I took the blue stars that were not seen by my Koopman operator. And starting from the blue stars, I predicted what will be the next point. And it does a fairly good job of prediction. I mean, taking into account that this is chaotic and this is data that's not been seen, it works really nicely. And if you want to compare this with Havoc, Hankel view of chaos, Havoc uses a Hankel approach where you're using the last element of your delay coordinates for as a driving function. I mean, this is rooted in Taken's embedding theorem, but you need an order dynamics over 14. And here you get away with smaller dynamics. Now, here's a more interesting problem. This is an actual practical problem based on real data. Okay? This is an experiment done with E. coli that are being grown in a medium that has a little bit of glucose and a lot of lactose. Turns out that the bacteria love glucose, so they start eating it, and of course, they run out of glucose. They can also survive on lactose. So once the glucose is gone, they switch to feeding on lactose. But to do that, certain genes have to be expressed. Okay? And what you're seeing on the left, it's a false color image of the genes that are being expressed. There are about 2,000 promoters for the genes over about 100 epochs. So there are about 20,000 data points. And the goal here is to detect when do the bacteria stop feeding on glucose and start going to lactose. I mean, at what point do the genes get promoted? That's called deoxic shift. And this is an example where I don't really care about going from state space to the observables and back. If I can do the segmentation based on the embedded data, I'm done. And this is exactly what you're seeing here. Green, it's when they're feeding in glucose. There's a transition in here where you don't know what's going on. Then blue, it's when they're doing lactose. And then in here is when they start running out of food. And then black means they're dead, essentially because they're out of food. And how do you do this? I mean, you just find the dynamics on the embedded manifold for a short horizon, and you just keep sliding your dynamics until it doesn't match your data. That's where your deoxic shift happens. Works beautifully, and I have the ground truth. This actually nailed the shift exactly what it happened. Here's an example from computer vision. Let's see. All right, for some reason. Okay, so two people walking. Just all there is to it, it's two people walking. Okay, so you project into the manifold, and what you're seeing in here, for some reason my computer is slowing down, but okay. Let me see if I can get. So what happens in here is the following. All right. Let's see if we can get it to work again. See, they crossed, and the lady is actually occluded by the gentleman. So when you actually project on the manifold, what you can see here is that the place where we don't have data about the lady moving. So we got our linear dynamics, and we just did interpolation. I mean, we identified the dynamics in here, and we just interpolated, and then went back to the manifold. Sorry. Okay, just bear with me for a second, because my computer, it's for whatever reason, it's slowing down. Okay, it sort of, well, show it once. Anyway, I mean, you can see it in there. We can actually make the person in the foreground disappear, inpaint the lady, and make it so that it looks like the gentleman in the front was never there. And so this is kind of a cool application. I mean, it's a big application for computer vision, but okay. So I told you this was going to be a short talk. So take home message. I can try to find Koopman operators using a structured semi-definite program. The complexity of the semi-definite program depends only on the spatial-temporal connectivity or order of your dynamics, and how large are the domains where you want to sort of preserve the geometry. But more importantly, in many, many applications, it's enough to find the embedded manifold. In other words, it's enough to find what your observables should be and the dynamics for the observables. And you don't even need to bother with other things. Okay? So something that I'm looking into, and I will welcome help from this group, is what happens when you have controls. Okay, and I'm sure you're aware of this, but there's a really cool example, again, from Sam Otto and Clancy Rowley, that says, look, if you have actuated systems, you're out of luck. A Koopman operator may not exist. And that's a simple example they gave, right? But they also noticed that you don't have embeddings for linear dynamics but you can find embeddings whose your dynamics are bilinear. So instead of looking for linear dynamics, look for something like this, where now you have the product of the controller input and the latent variable. So the point is, in that case, we need algorithms to identify bilinear systems. More so, if I want to use this approach, I need to do this using kernel-based approaches. I've been working a little bit into that. I don't know how to solve the problem. So if you guys know how to deal with actuated Koopman, I would really want to hear your thoughts. And that's it. It's a short talk because I really want to have a chance to discuss with this group. Many thanks for inviting me. And of course, as usual, my name is doing presentation, but this is the work of many people in my group, postdocs, students, and thanks to the funding agencies. So that's about it.
Thank you.
All right, let me, okay. Right. Okay, so, oh, no, I don't want this. All right, so questions, or can I ask questions to you guys, or?
Well, I have a question. So first of all, my name is Michael, by the way. This is great because, you know, as you figured out, we desperately need principled ways of choosing observables, right? And this seems like you didn't talk about computational costs as much, but it seems like, you know, way more efficient than a neural net based method, which exists out there. So what can you give me an idea of the computational complexity?
Yeah, it's a computational complexity to solve in your SDP. So if you use a chordal decompositions, it's the number of clicks that you have times the size of the click cube or so. But one thing I want to say, this is a one-shot, shallow method. I mean, with neural nets, you need lots of data and hope that everything works. In here, either it works or doesn't work. You look at G, and if G is rank deficient, it worked. If not, it didn't work.
Yeah, definitely. Thank you.
Okay. Thanks.
I have one question on the Lorentz. Have you tried parametric study with more than one step ahead? And the question is, I guess, when does one lose predictability?
I didn't try, but I mean, you do it very quickly because it's chaotic. I mean, I have another systems where like predator prey, it works really well.
Yeah.
But I mean, in the Lorentz, it also depends because I mean, I was being lazy here. And if you notice, I took points on the same trajectory or close to the same trajectory I used for training, not the training data, but points in the same trajectory. If I wanted points not in the same trajectory, I would have had to have more training. But that's a very good point. So
it's actually kind of a lead to a further point, right? In that case, we know that. Let me start with this. So, in principle, one can find the finite dimensional linear representation, as I tend to call it, if and only if there are eigenfunctions.
Right.
And in Lorentz, actually, we rigorously know since about 2009 that there are none. And
right.
Actually, maybe this is just an interesting side comment, which is the way this was proven is to prove that there are no eigenfunctions of the Koopman operator. The way the mixing in the Lorentz attractor was proven was to prove that there are no eigenfunctions, which translates to the fact that there are no finite dimensional linear subspaces. Now, one can approximate, and one gets, you know, a noise, perhaps a noisy residual. But in that case, the predictability also might be determined by the Lyapunov exponent.
Right. So,
yeah,
Igor, I mean, I entirely agree with you. And that's why I cover my basis saying, what happens if your dynamics G is not rank deficient? So, I mean, the smallest singular value of G tells you how close you are to actually having linear dynamics. So, but I have not explored the connection of, suppose that I know that G, my error is bounded in the linear subspace by this. How does that translate to the other one? Because I would have to run this, in my case, through the loaner and find out things. So that's essentially why I'm doing one step ahead.
So the additional kind of comment I think that could be interesting is some kind of a combination, because I really like the, as Michael also said, I really like the structured approach, right, to finding these things. But one interesting connection it might be, and maybe we can talk about this after the fact, is combining it with this idea of conjugacy. So if you actually have eigenfunctions, then I don't know if you've seen this, but we've done this a little bit of this with a group at Caltech, Joel Burdick's group in robotics, or a drone flight, right? And so the idea was learn the nonlinear, so learn the eigenfunctions of the nonlinear dynamics, create a linear system, design there, and then port back.
Okay.
And so what would be interesting here, additionally, I think, would be combining these two things, because even in chaotic systems like Lorentz, there are actually very structured observables. So Milan Korda is here. And so we have a paper in which you can find these observables that have a much longer predictability horizon than the native variables. It's just kind of an unstructured,
no, that's
a little bit of an
wonderful.
unstructured remark, but I was exactly hoping that these kinds of tools from systems theory can be used here, and you're showing that. I think if they're combined with conjugacy, they might become even more powerful, notwithstanding all the remarks that you gave on scaling and things like that, which sure, but the essence is a very powerful tool, right? For kind of dynamics.
So Igor, I noticed that the paper you submitted to CDC, now it has conjugates in the title. Is that a good place to learn?
Yes, that's a brief place. There is my own paper from about 2019, in which I think this is hopefully described reasonably. I'll send it to you.
Perfect.
And then I'll send you the robotics paper in which they actually used machine learning to learn the conjugacy.
Okay.
And so the essential idea is that there are variables in which the system, observables in which the system actually is linear, provided that it doesn't have continuous spectrum. That's actually a theorem. I'll send you another paper.
Okay.
So the idea is, okay, if we find those, then all the systems tools can be applied directly. And so what I'm interested in is whether the methodologies are finding eigenfunctions in principle. It's very spectral as a point of view, right? But it's kind of an interesting way of viewing things. I mean, Alan Chow is also here. He was in my group as well. He's in my group as well. And we were talking yesterday about when are time delay variables in fact eigenfunctions. And they are for rotations. So if you have toroidal rotations.
So how does this connect with Takens?
Yeah, that's exactly connected to Takens theorem. So yeah, I'll send you a few papers in which, so the first time Takens embedding was used in Koopman is actually way back in 2004. Actually, when I worked with Andrzej on the jet engine thing, you will see it in that paper.
Okay.
So it's very natural. Takens and Koopman connection is actually a very natural connection because Koopman evolves by composition and Takens embeds by composition. It's the same thing.
Right.
And so we've been using these time delay variables in the Hankel sense to provide the observables as well.
Okay. Before I forget, I need to find out, but there's a paper where they show that for certain classes of systems, the Kalman linearization ends up being exact. So this is also interesting because I mean it's related. You could do Kalman linearizations and find your linear dynamics from linearization, and for a class, the dynamics has to be polynomial. But for polynomial dynamics, you can actually get exact linearizations, and you can bound the number of delay variables that you have to take ahead of time. So
yeah, if you have this is quite interesting. I mean, Kalman is really encode, or rather a representation of Koopman in some sense, just in a polynomial basis.
right.
It really is just Koopman. Actually, Kalman knew about Koopman and writes it in his original paper. He says, Koopman came up with this before me. I'm just doing it in polynomial basis. So there is a very tight connection, but if people have done some work on estimating, the closure, as I would call it, that's quite interesting. I don't know that I've seen those. So
Okay, I'll look for the paper. I mean, it's a paper that doesn't have anything to do with this. It has to do with computing variance sets, but hidden in the paper, there's actually a proof that the Kalman linearization is exact. And I don't know if the authors realize that in their version or not, but it's, if you know what you're talking about, I mean, it jumps at you. So I'll send you the paper.
Okay, perfect.
So now you have to tell me about actuated Koopman operators. What have you done on those?
There is quite a bit this work, and actually people that are on this call can talk quite a bit about this. It started probably with a paper that Milan wrote with MPC. I don't know if you've seen that one, right?
Yeah.
Okay. But then, and there is Milan. But then so let me go through a jump, because recently we got into doing a very interesting application, which is in soft robotics. And so Erwin on top left has been on the hardware side of this, and then and also applying Koopman, to this as a control, and then Michael and Alan, I don't want to forget anyone in this context. So we have quite an interesting application. I don't know, Erwin, if you want to show the video, but you might not want to. We might want to stop recording because it's not submitted yet.
Yeah, I can.
So